Hello, today we are going to talk about critical points and inflection points. Today we need to understand critical points and inflection points. We can determine if a function has a local max or min, determine if a function switches concavity, and we want to be able to apply the first and second derivative tests. So let's just refresh our memory with what we know about the first derivative compared to the function. So my first derivative, if it is positive, we know that my function would be increasing. If my first derivative is negative, then my function is decreasing. Remember, first derivative is just slope. If you have positive slope, my function increases. If I have negative slope, my function decreases. All right, the second derivative tells us about concavity. If my second derivative is positive, we are concave up. And if my second derivative is negative, my function is concave down. Okay. We also know that if this second derivative is positive, then that meant the first derivative was increasing, because the second derivative is the slope of the first derivative. And if the slope is positive, the derivative is increasing. The second derivative is negative, then the first derivative would be decreasing. All right. Using the first and second derivatives to find local minimums and local max. So if you think about this, the first derivative is slope. So when your slope changes from positive to negative, you have a high point. Call that a local max. Right? Positive slope, negative slope, that was a local max. Positive slope, negative slope, local max. So on a local max, f prime switches from positive to negative. Vice versa, if you have negative slope and you go to positive slope, you have a local min. Negative slope, positive slope, local min. Negative slope, positive slope, local min. So to get a local min, f prime switches from negative to positive. All right, we are going to define critical numbers today as a function, for any function f, a point P in the domain of f, where f prime of P equals 0, or where f prime of P is undefined, is called a critical point. So we take our derivative, we set it equal to 0, and that's a critical point. Or we have our derivative where it's undefined, and where derivatives are undefined is if you have a sharp corner. So we have the first derivative test for local max and local minimum. A critical point C, if f prime goes from positive to negative, the first derivative test tells us that we're going to have positive slope and then negative slope, so that will be a local max, like mentioned on the previous slide. If my f prime goes from negative, so if I have negative slope, I look at a function that's negative slope and then it turns positive slope, you can see that will be a local min. If f does not change sign, then we have neither local max or local min. So the first derivative test tells us if we have a local max or a local min using the first derivative because it deals with slope. Our second derivative test is going to deal with the second derivative. And the second derivative deals with concavity. So case 1 says that our first derivative equals 0 and our second derivative is greater than 0, then we'd have a situation where we have a function that's concave up, and at C, the first derivative equals 0, and so this will create a local min. In case 2, we have our second derivative being negative, less than 0, so that means our function was concave down. Oops. And so if our first derivative is 0 at C, let me draw that again. So I have a concave down, and then the first derivative is 0 right there because the tangent line is horizontal. Then we have a local max. And then case 3, we have where they're both 0. So the first derivative 0 and the second derivative 0. We cannot determine if we have a local min or max. Local extrema. And so that's because if we just think about two different functions like x cubed, right? If I look at x cubed, the first derivative, 3x squared, at 0 is 0. And the second derivative, which would be 6x, at 0 is 0. But you can tell that right there, that is neither a local min or a local max. However, if I had the function y equals x to the fourth, kind of looks like a parabola, just fatter, or more wide at the bottom here. We can see that y prime would be 4x cubed. And so y prime at 0, the first derivative at 0 is 0. Right? The slope of that tangent line is 0. Right? And if you do the second derivative at 0, so the second derivative would be 12x squared. And at 0, we get 0 for the second derivative as well. But here, it was a local min. So we have to do more investigation, is what I'm saying. The second derivative test tells us, case 3, we need to do more we got to find more information out. Case 1, we know that we're going to have a local min. Case 2, we know we're going to have a local max. But case 3, we need to do further investigation. So you heard, I threw out the term extrema already. Local extrema just is either the local max or the local min. So it includes both terms. So when you say local max and local min, and you don't want to say both of those words at once, you just say local extrema. All right. So at critical points, you may have local extrema. The big key there is may. Remember, critical points are where f prime of c equals 0, so some point, so the derivative equals 0, or the derivative's undefined. Okay, it may be a critical point, but it's not necessarily, right? So you can see if I look at x squared, right, that would be a critical point. The derivative would equal 0. But when you look at x cubed, like the last one, the derivative equals 0, but that is not a local min or a local max. That's neither. Okay, so critical points may happen, but extrema can only occur at critical points. So this is like the argument, every square is a rectangle, but not all rectangles are squares kind of idea. So if you know you have a local extrema, it will happen at a critical point. If you have a critical point, you might have a local extrema. Now moving on to inflection point. An inflection point is just the point on the graph where the function changes concavity. So a function goes from concave down to concave up. Right here would be your inflection point. And we tell inflection points by the second derivative. So here, the second derivative would be less than 0 because it's concave down. And here, the second derivative would be positive because it's concave up. So inflection points are where the second derivative, so f double prime, switches sign. We had to be a little bit more particular on local mins and local maxes. We had to say switch from positive to negative or negative to positive to determine if it was a local max or a local min. But when we're looking at inflection points, we only have to say it switches signs because it doesn't matter if it goes from concave down to concave up or concave up to concave down. That's still an inflection point. So that would be where the second derivative is positive. Here would be where the second derivative was negative. Right there is my inflection point. All right, so here's just an example to mark critical points and state whether local mins or local maxes. If I was in class today, we would do this as an activity. So we can see a local, take a minute, pause the video, do this on your own. Okay, hope we are back now. Let's see what we got for answers. So critical points on F, remember that's where F prime equals 0 or F prime is undefined. So you're looking for slopes of this graph because this is the graph F. So where's the slope 0? Well, the slope 0 there, there, there. All right, and where is your slope undefined? Right there. It's undefined. Okay. So your critical points are going to be at, well, 0, 5, x5, x7, kind of looks, and x9. State whether each is a local max or local min or neither. Okay, so you can see that 0 is a max, x7 is a max, x9 is a local min, and x5 is a local min. Now if I switch it on you and not tell you this is f, but this is f prime of x, you want to find critical points. You are looking for where f prime of x equals 0, which is here, here, and here. And remember, critical points, we want to state whether they're min or maxes. So we have to think where they switch sign. Okay. Going back to number 1 real quick, f prime equals 0 is the only thing we're going to be worried about here because there's no place on this continuous function where it's not differentiable. It's differentiable everywhere because there's a value on everywhere in that blue graph. Okay, remember, this is the derivative. So we're looking at the points where it crosses the x-axis. That's where the derivative equals 0. All right, so here, this guy, the derivative went from positive to negative, so you think your function's going to go from positive to negative, then this is going to be a local max. And here, your slopes are negative, so your function was decreasing, and then your function was increasing. So that's going to be a local min. Here, your slopes are positive always. So that means your slope, your function was increasing, increasing, did not increase or decrease, and then kept increasing. So this is neither. Okay. So moving on to 3, it says find the inflection point. So that's where your second derivative switches signs. Not where it equals 0, but where it switches signs. And so if you're looking for the second derivative is the slope of the first derivative. All right, and so I want to know, where does the slope switch signs? Well, it looks like the slope of this is switching here at 0. And then it looks like the slopes are switching here at x5. My slopes are positive, then my slopes are negative, and so that's happening at x7. And then again at x9. All right, and then it stays positive the rest of the way, so those are my inflection points. All right. On this one, we want to figure out which function is the function, the derivative, and the second derivative. And again, we want to do this by thinking about slopes and positive and negative and concavity. So we want to take a moment here and think about which one's doing which. I want you to stop and think about which one's doing which. All right, hopefully you've had some time to reason things out. If I think about the blue graph being, if the blue graph was the first derivative, I'm just putting it up here, it's not. That means you would have a function would have to always be increasing. So is either the red or the green always increasing? No. So therefore, the blue cannot be the first derivative. Similarly, it can't be the second derivative either, because it's always positive, right? The blue graph is above the y-axis, except for right down there. But it can't be the second derivative either, because that would say the red graph or the green graph would always be concave up, because the blue graph is always positive, right? And if your second derivative is always positive, your function would have to be concave up. So that really only gives us the idea that blue has to be f of x. All right, then I think about which one's the derivative, which one's the second derivative. So you can see this blue graph is increasing, 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 increasing. Up to this point, my function's increasing. So that means my first derivative has to be positive all the way up to that point. And the green one is the only one that is positive values up to that point. Okay, so that is the only way we can say that's our first derivative. And then you can see your function here is decreasing all the way, which means my first derivative has to be negative that whole route, which it is. Which leaves this guy, the red one, to be my second derivative, which is concavity. All right, and so if you look at this graph, you can see right about here on the blue graph, it switches from concave up, so it looks like it's concave up, which would mean the first derivative, or sorry, the second derivative would have to be positive, which it is, you can see that. And then right about there, it switches to being concave down, and that's why the second derivative goes negative, up until right about there where it switches back to concave up. All right, so I would like to have you give it a shot, the homework, and we will come back and pick up some pieces when I get back on Monday. All right, have a great day.